Hi, everyone. Welcome back. Today we have Ali Shirali speaking our seminar. Ali is currently a PhD student in the computer science department at UC Berkeley. He is advised by Rediat Abebe and Moritz Hart. Ali is interested in the social aspects of machine learning. In particular, his work has covered how humans are involved in the life cycle of machine learning, from data annotation to evaluation, and how humans are affected by algorithmic systems, specifically the interplay of algorithms and inequality. And today, he will tell us about breaking inequality barriers through mutual connections. Ali, take it away.
Thank you for the introduction. Hi, everyone. I'm Ali, and I'm going to talk about this long title, so let me explain it in a bit. I'm going to talk about social network where different communities are formed and probably segregated. And I'm going to study a very natural mechanism where individuals find their new friends through the friends of friends. This is called triadic closure. I'm going to study this mechanism and how it can desegregate the network and make the different communities be closer to each other. So this is a joint work with Rediat, Nicole, John, and Brandon. Let's get started. But before that, feel free to interrupt me at whenever you have any question. I will be more than happy to answer them. Okay, so we have a heterogeneous networks where individuals have different types. I have color encoded types, so each individual has a single type. This is an important assumption, actually. And just like many real-world networks, we can see that the network I have here is segregated into three maybe communities. And this is not something we would like to see, because if different communities are already quite different in terms of inequality, such a segregation is going to just amplify the existing inequality. So we would like to push back against this segregation and make the communities become closer to each other. But to do that, we probably need to know why segregation has happened. One of the common factors often cited to be responsible for such segregation is homophily. What is homophily? Homophily explains that why individuals have a tendency to become friends with similar ones. For example, here in this figure, this guy at the center has more red friends than other types. So clearly, having homophily in a network results in segregation. But homophily is something natural that probably we cannot change it directly. And in the case we want to push back against homophily, we need to know maybe other natural processes which are interacting with network segregation. And that's the topic of my talk. I'm looking for another social process that might change the effect of homophily on segregation. So what is this process? It's very simple. It's called triadic closure. I'm going to explain it. Let's look at the network we had. We got, let's say, three individuals like this. Two of them are not yet connected, but they have a mutual friend. And we call such a structure a wedge. And triadic closure simply says that wedges are likely to be closed. This missing link is gonna likely to be disconnected. This is what is called triadic closure, and I'm sure you have seen it everywhere. I don't know, for example, this kind of recommendations is very common, like this who to follow in Twitter. For example, here, this guy is me, and I and Black in AI account both have my co-author Rediat Abebe as friend, as connection, and I have been recommended to follow Black in AI. So these kind of recommendations and these kind of connections are very likely to be seen in practice. That's why it's worth understanding if this natural social process is going to make the network more or less integrated or segregated. Okay, so let's have a little bit of formalism. periodic closure simply says that wedges are likely to be closed, but there is a subtlety in this definition that I have found it a source of confusion in the literature. We can have different types of wedges. Wedges can be monochromatic or bichromatic, depending on whether the missing link is between agents of similar types or dissimilar types. And you can take it as definition, but triadic closure says that wedges are equally likely to be closed, regardless of being monochromatic or bichromatic. So let's take this definition and see what happens. But before that, let's look at the social science literature, for example. It's commonly known that periodic closure and homophily works in tandem. For example, Kossinets and Watts have mentioned that periodic closure effectively constrain the opportunities, or more recently, Asikainen and others have mentioned that homophily will be amplified by triadic closure. Even more recently, Toth and others have mentioned that homophily and triadic closure work together, and these two forces sharpen social segregation. So there seems to be a consensus around the effect of triadic closure, and that might make sense. But today, we are computer scientists. I'm going to make it formal, and I'm going to investigate it, actually. Is this intuition, is this common social science intuition correct or not? That's what is coming up. Okay, let's define. I'm just talking about segregation, but let's make it formal. I'm gonna define the opposite notion of segregation, which is integration. We want the network to be more integrated. And network integrated is simply the fraction of bichromatic edges we observe in the network. Bichromatic edges are edges between agents of dissimilar types, highlighted here. So let's say this is the definition of network integration, and I'm going to study the effect of triadic closure on network integration as defined by this specific measure. But I think I would like to give you some intuition before getting to the theorems and results on why do people think actually triadic closure amplifies homophily. Let's say Bob is just a new agent, just arrived. Because of homophily, he's going to choose, let's say, 2/3 of his friends from the blue types. Let's say I have two types, blue and red types. So Bob has initially chosen 2/3 of his friends from the blue types. And then because of homophily, we might expect that Bob's friends, friends of Bob's friends are also likely to be similar to them. So here, every single initial Bob's friend has 2/3 of her friends from similar types. And now let's say I would like to see a new connection by triadic closure. Who are the candidate new friends? These are all candidate new friends. And if you look at the initial friends, 2/3 of them were similar. And if we look at the candidate friends likely to be closed because of triadic closure, again, 2/3 of them are similar. So apparently, with this simple intuition, triadic closure is just going to replicate the existing homophily. This is not something maybe we would like to see. But that's somehow the intuition behind all those claims why triadic closure might amplify or might just replicate existing homophily. And it's a natural intuition, actually. But is this intuition complete or not? I'm going to give you an alternative intuition. None of these intuitions are actually complete. I'm going to make everything solid by proposing some formal models. But let's look at an alternative intuition which gives us somehow an opposite result. So in the original intuition, I actually cheated a little bit. As you can see, none of the Bob's three initial friends are actually themselves friends with each other. I'm somehow just neglecting the existence of other agents. But that might not be necessarily the case. Let's say in this example here, this is the whole network Bob sees, and he's going to choose 6 new friends like this. And because of homophily, again, 2/3 of them are similar. And now let's say we would like to see how would triadic closure adds to this homophily at this step. So for the candidate new friends that the Bob can find through his current network, these are the candidate friends, candidate new friends. And as you can see, these are just half of them blue and half of them red. So apparently in this case, where Bob's initial friends had some connections themselves, it seems that the candidate new friends, the remaining candidate new friends are actually less homophilous. In other words, if Bob is not yet connected to someone, that might be because they were dissimilar. So if he's going to choose a new friend based on friends of friends, that new friend might be less likely to be similar. No problem if you didn't catch the intuition, but the intuition is simply this. So these different intuitions actually result in different conclusions. The first or original intuition simply says that triadic closure is going to replicate existing homophily. The second intuition says that adding a new edge via triadic closure is going to actually decrease. It's going to compare to existing homophily. Is going to decrease existing homophily. It's going to push back against existing homophily. And the big question is which intuition is correct. And surprisingly, maybe I'm gonna argue that the original intuition is just less accurate. But none of these intuitions are actually complete. Okay, let's have some formalism. Let's start from the simplest case. We have a stochastic block model. What is a stochastic block model? We have some types here, 3 types, for example, color encoded. And the probability to observe an edge between agents of similar types is P. And the probability to observe an edge between agents of dissimilar type is Q. And we say a stochastic block model is homophilous if simply P is larger than Q. So that's a very simple model, a static model of the network. There is no triadic closure here. We're gonna to add it, but that's the simplest definition we can have about how a network is formed. And this is our main question: how would triadic closure change the network integration? In order to measure the effect of triadic closure, I again need some definition here because this model doesn't have triadic closure. What does it mean? What's the effect of triadic closure? So I have to add it post-network formation. So I assume that this network G is already formed, and now the agents decide to find new friends through their current connections. So as I define triadic closure, all wedges in the networks are equally likely to be closed. So what I'm going to do is choose a random wedge uniformly at random and close it. For example, this wedge here, and call this network G prime. And then let's define the effect of triadic closure to be the difference of integration in network G prime and G. A simple definition. Actually, we should use the expectation here because I'm choosing a random wedge here. So there is always an expectation behind all of the equations. I drop them for simplicity. If this is how we define the effect of triadic closure, we can have this very general S-strong theorem for sufficiently large stochastic block models with 2 or more types. periodic closure is going to have positive effect on network integration as we just defined it, if and only if there exists homophily, if and only if P is larger than Q. And you see, this theorem is in its most generality. There is no assumption about the probability of different types or something else. And that's quite surprising. This is actually against all the claims I mentioned. But, you know, you might say, okay, wait, Ali, maybe the effect you observe is because G prime is simply has one more edge compared to G. Maybe that's why you see this general effect. And yes, that might be the case. That's why I call the notion of effect I just defined as absolute effect. And now I'm going to define another notion of effect, which is called relative effect. So in absolute effect, I had a network G. I closed a random weight, obtained network G prime, and then looked at the difference of integrations. In relative notion of effect, I'm going to consider a baseline mechanism. Let's say we have a baseline mechanism that just adds a random edge to the network. For example, this edge here. And I call the obtained network G double prime. Then I can compare the integration of G prime to G double prime and call it relative effect. This is the effect of periodic closure compared to a baseline mechanism. So what is a good choice of a baseline mechanism? What we considered is just as this simple baseline. We call it adding a gamma homophilous random edge. What does it mean? Among all those missing edges, the missing links, I'm going to choose one of them at random, but I'm going to weigh up monochromatic missing edges by a factor of gamma. So it kind of reflects some level of homophily. So this is the baseline. I'm going to close the random edge, but monochromatic edges, which are edges between agents of similar types, are more likely to be chosen. And what do we observe? Somehow consistent with the previous results. Again, if the stochastic block model is sufficiently large, and if we have two or more types, compared to the baseline I just proposed, this baseline of closing a gamma homophilous random edge, periodic closure can have positive relative effect if this condition holds. And I'm not going to show you the closed form of this upper and lower bounds, but what is interesting here is that there is no P and Q in U and L. So the only dependence on P and Q is their ratio. And what we need to know is that U is larger than 1, the lower bound is less than 1, and they're both monotonic in the parameter gamma. And intuitively, we can say triadic closure has positive relative effect if and only if the network is neither very homophilous, which means this ratio of P over Q is not very large, nor very heterophilous. Heterophily is just the opposite of homophily. So yes, as long as the network is not very homophilous, we can expect triadic closure to still have positive relative effect as well. And that's interesting because, yeah, so far we observed that the triadic closure, unlike the common intuition that social scientists have, can have positive effect. If the network is homophilous, if you're using absolute effect, and if the network is not very homophilous, if you're using this just relative effect. Okay, I'm gonna move on to the next model I have, and you know this stochastic block model is very simple, and you might say that the results are just very specific to this notion of network model. So I'm gonna generalize it, but before that, let me know if you have any question. I'm gonna wait 3 seconds.
Yeah, a quick question. Is the natural value for gamma P over Q, which kind of sounds like you're taking one more edge from basically the same distribution again? And what do your results say for that specific value of gamma?
Yeah, that's a good question. What should be a natural choice for gamma? I think it really depends, but yeah, that might be a good choice. P over Q or something from the order of P over Q. If we choose it P over Q, then this condition, if we choose it just P over Q plus epsilon, I think this condition always holds. Otherwise, it never holds. And that's kind of a very critical value. So yeah, I think a natural choice for gamma will be something proportional to P over Q. But it really depends how do you want to define your baseline. And that's actually a drawback of this notion of relative effect here, because it always depends on how do you define the baseline. But yeah, the other thing to observe here is that if you choose your baseline to simply add a random edge, being blind to the edge being monochromatic or bichromatic, then the effect will be reversed actually, because P over Q is always larger than 1. But that's, that might not be the case for you. What I didn't show you here is if you choose gamma to be P over Q, what is this factor? What is this parameter U here? Yes, I don't have it here, but it really depends on your network structure actually, yeah. But yeah, if I remember it correctly, this P over Q is somehow a critical value. That kind of changed the sign of the yeah, I hope I have answered the question.
Thank you.
Okay, so so far I have used a simple model, stochastic block model, and I just studied a very specific notion of integration. But a criticism might be that is this also true for other notions? I don't have a general answer for that, but what we were able to show is that if I consider a network with 2 types, one of the type is just the advantage and the other one is just the disadvantage type, and I look at the expected eigenvector centrality of the agents in each group, I'm going to observe exactly similar results. I'm going to observe that the gap between these 2 groups is going to be smaller if I use triadic closure or if I increase the contribution of triadic closure. That's interesting because somehow these centrality measures are quite independent from the integration measure I have here. But it's just interesting to mention that similar consistent observations hold when I use another measure. But there might be a case you find the measure where triadic closure has opposite effect, and I cannot deny that. The other thing is that, yeah, the stochastic block model is very simple, and that's why I'm gonna generalize it to a popular dynamic model in economics, the Jackson-Rogers model. This is the next thing to observe. So what is Jackson-Rogers model? Let's say we have only 2 types, just for the sake of illustration, but the results and the model are more general for any number of types. So Jackson-Rogers model, it's a dynamic model in the sense that new nodes always arrive and make new connections. And it has 2 phases. In phase 1, let's say this new agent, Alice, has just arrived. And this is the current networks. These circles are the current networks. She's going to make NS new connections from agents of similar type and ND new connections from agents of dissimilar types. That's the first phase. In the second phase, Alice is going to choose her current network and choose friends from the friends of friends. This is exactly triadic closure. So she's going to choose NF new friends in phase 2, where alpha proportion of them are chosen from the friends of similar friends, friends of initial similar friends. And the rest are chosen based on, the rest are chosen from the friends of dissimilar initial friends. So this is how the model is defined. And we can simply see that homophily in phase 1 is simply NS is larger than ND. But what is homophily in phase 2? It's not very clear because this, friends of similar friends are not guaranteed to be similar. So it's actually vague how to define it, and it might depend on this factor alpha. The good news is that the results I'm going to show you do not depend on the factor alpha here, and do not depend actually on homophily in phase 2, as long as we have a reasonable assumption about alpha, like alpha being larger than half here. So the only thing I'm going to need is homophily in phase 1. And that's our main question again: how would triadic closure affect network integration in Jackson-Rogers model? Unlike a stochastic block model where I had to, triadic closure was not there, I had to add it post-network formation. The good thing about Jackson-Rogers model is that triadic closure is already there. The second phase is simply triadic closure. So all of those controversies around how to choose the baseline, how to add a new random weight, they don't exist here. And all I need to do is to change this number of phase 2 friends and F and see how the integration changes. So this is how I define absolute effect. I'm going to keep everything fixed, and I'm going to change the number of friends in phase 2 and F. And then I'm going to look at the integration in equilibrium. When I change something, this is a dynamic model. I have to wait to see some equilibrium. Again, because I have kept everything fixed and I'm increasing phase 2 friends, I'm increasing NF, you might say that I'm increasing total number of total number of connections. So again, I can define something to adjust that. I call it relative effect, where I increase NF, but concurrently I also decrease initial friends. I also try to keep the composition similar. So I'm going to keep the total number of friends fixed, also the composition of the initial friends to be fixed. This is how I define relative effect. Then I change NF and look at the change of integration in equilibrium.
Are you looking at the network integration before and after phase 2, which is when triadic happens, or
no? Actually, no. Yeah. No. What I'm gonna do is that, let's say I have 2 different networks. They started from some point, and the probability of arrival of the arrival types are actually similar. So somehow similar agents are joining this network, but the difference between 2 networks is these parameters. One network has, for example, larger NF, and I'm gonna look at the integration of these 2 networks in equilibrium. So yeah, I'm not looking at integration before and after phase 2. I'm looking at the network integration after a lot of agents have been added to the network.
But how does that answer the question of how would triadic closure affect?
So it's kind of a counterfactual question. You can say, let's say I want to do some intervention on my network, okay? On Twitter, I want to, you have already formed some connections, and I want to make some recommendations to you. And I would like to know if this NF is something I can intervene on. I can decide how many new recommendations I can give you based on triadic closure. So the question is, if I increase NF, is I increase the number of recommendations based on triadic closure, is it gonna change network integration or not? That's the question we would like to answer. Yeah, thanks for that. So interestingly, the results here are actually more strong and more general than a stochastic block model, because for any Jackson-Rogers model, for any number of types, as long as this condition holds, alpha is just larger than 1/k, periodic closure has both positive absolute effect and positive relative effect, if and only if the first phase is homophilous. And that's quite interesting. If it's just the first phase is homophilous, and if you increase the second phase contribution to the network, you're going to have a more integrated network in both the metrics I defined, both absolute and relative sense. And that's quite interesting, and against maybe intuition social scientists have, and that's a very strong effect actually. Okay, just before moving on, I would like to mention something, because in obtaining these results, we provided some analysis of the behavior of the network after convergence. Just would like to mention it. You don't need to read the theorem statement. But what we have here is that for every Jackson-Rogers model with these parameters, network integration is gonna converge to this simple closed form. That's interesting because we can play with this thing here. We also know the rate of convergence. And these results are actually very strong and very general, because that we have this closed form solution here. And you know, this is approximate because we have obtained it with mean field theory. But later at this talk, I will show that using some real world data, I will show that this thing is actually quite a good approximation of network integration after convergence. Just wanted to mention that there is a tool here which is really helpful to study Jackson-Rogers model. Okay, last but not least about the models. You know, our results are not only against intuition, they are also against a recent theoretical study by Asikainen and others. So I thought it might be a little confusing if you one day find this study and see the exactly opposite results. So I'm going to show what is different here and why we have obtained exactly opposite results. So far I talked about the stochastic block model. That was a static model. I also talked about Jackson-Rogers model, which was a dynamic model. And it was dynamic because new nodes were arriving in time and making new connections. And Asikainen and others have a different dynamic model. It is dynamic because the edges are changing during time. So we have a fixed set of nodes, but they are changing their connections. Let me explain their model briefly. Let's say this is my current network, and Bob is chosen at random to change one of his connections. So Bob has two options in their model actually. With probability C, he's gonna choose a new friend based on triadic closure, and otherwise he's just gonna choose a random person from the network. So this parameter C is somehow controlling for the contribution of triadic closure in network evolution. And then that's not it actually. These are just candidate connections and candidate links to be formed. Then this is this step actually, where depending on whether the missing edge, which is going to be formed, is monochromatic or bichromatic, it is going to be formed with probability S or 1 minus S. And in the case that the new edge is formed, because we want to keep the number of edges constant, Bob is gonna just drop a random edge. For example, here, he dropped this edge, or here, I don't know, he dropped this edge. So this is how the model works. A random agent will be chosen. He's gonna have two options, and for every option, there is this extra step here which decides whether this connection can be formed or not. But that's actually the problem, this step here, because the way we define triadic closure and the way I believe it is supported by empirical works, triadic closure does not distinguish monochromatic and bichromatic wedges. But here, depending on whether the wedge here is monochromatic or bichromatic, the probability to observe that edge to be closed is different. So we thought that might be the source of confusion and the source of different results, because triadic closure just has one layer of extra homophily here. And we thought maybe we can change the model. So, I forgot to mention that they consider homophily. Actually, homophily translates here to S being larger than half, which makes sense. Monochromatic edges are more likely to be formed. So we decided to change the model. And now we have homophily if we are going from the top path, but we somehow made triadic closure free from homophily. That's the change we made to the model. And interestingly, we could see consistent results with our model. We could see that if we increase the contribution of triadic closure by increasing this probability C, then we can see higher network integration if and only if there exists homophily, if and only if S is larger than half. And it's just very consistent with our results. So I thought I have to mention that, the way you define triadic closure hugely affects the conclusions. And that's all the results I wanted to mention. We discussed the stochastic block model, Jackson-Rogers, and Asikainen models, and in almost all of them, we could see some really good effects from triadic closure. But in the last few minutes I would like to show you some empirical study to maybe support our findings. Citation networks are known to be captured by Jackson-Rogers models. So I'm going to use citation networks from some sources. It's a very limited period with almost 1.5 million articles. Here, articles are nodes, actually. So citations are edges, directed edges, and articles are nodes. And we have to define some types for our nodes because we studied heterogeneous networks. So for every article, we know what field of study this article is from, and we simply choose. And in the data set, we have some weight which says this article can be corresponded to this specific field of study. So I'm going to define node type a single number, which is what field of study this article is most likely to be from. So we have articles as nodes, and node types are field of studies. And as I mentioned, that this is a good network to study because previous studies have shown that the dynamic of this model can be captured by Jackson-Rogers model. This is a directed graphs, nodes appear sequentially and never disappear. And it's maybe how researchers find new works. They maybe initially find some articles, and then they look at the citations and find related works. So it's very natural to assume that the Jackson-Rogers model is somehow capturing the dynamic here. And what I'm gonna do is, the results we had in Jackson-Rogers section are based on this theorem, which somehow explains the behavior of networking after convergence. So I'm going to evaluate this argument here. I'm going to evaluate if if I can predict network integration after convergence with these few parameters. So to evaluate this theorem, I need some estimation from the network parameters, and it's not at all straightforward to estimate them. It's really hard because we only see, let's say, a network like this. Article U has cited V, W, and X, and this is the citation network. And let's say I want to estimate NS, ND, and NF, and alpha. These are 4 parameters of the X-Rogers model. But I really don't know which of the citations are formed initially and which of them are formed from triadic closure. Just let's look at these 3 connections here. There might be 3 possibilities. Maybe all of them are formed in the first phase. Maybe just, I don't know, this last citation is formed at the second phase because W had cited X. So we really can't see which connections are formed at what step. That's why we have no assumption about that. We assume all the valid configurations are equally likely. We also consider some priors for these parameters and do some maximum likelihood estimation, which I don't go through. But let's say we do some assumptions, some really simple assumptions, and obtain some estimation from the network parameters. Then what I can do is to look at the network evolution during time and see maybe after a change or something, I can predict the level of integration. I can predict the level of integration after equilibrium. Okay. Yeah.
So these parameters also depend on the choice of U as well, right? Like which node I want to look at to.
Oh, yeah, actually, but I assume that all nodes have common parameters. So here I only showed U, but I should do it for V, W, and X as well. So these are common parameters for all the nodes. Yeah. And of course, because not all papers have similar number of citations, this is not exactly the model I explained. That's why I consider a prior over NS, ND, and NF, and assume that NS, ND, and F and alpha are drawn independently from a prior for each node. And then I try to estimate the mean of those priors. That's how it works. But yeah, so good point. Thank you for asking. So if I want to evaluate this theorem, this integration in equilibrium, that theorem just gives me a single number, and it's really hard to evaluate based on single number. So what I try to do is just maybe to cluster fields. To cluster fields, the data set we have has a lot of different fields which are somehow independent. So I try to do some clustering here and neglecting the connection between clusters, so I can study each cluster independently. Then I will have one prediction per cluster. Also, because clusters are diverse, I'm going to have some variation across clusters, and these two actually let me to do a stronger test. I will have more number of predictions, and these predictions are more diverse. So what's the results? I'm going to show you a simple result we have just for illustration. I'm going to show you a figure like this. On the x-axis, this is the true integration. This is the observed integration after equilibrium. This is something we wish to be able to predict. And on the y-axis, this is something that the theorem predicts. And I have a couple of clusters. For example, I have electrical engineering. These are all articles from electrical engineering. And I have some arrows like this, which say at the beginning of the period, I'm studying the network. This is the observed integration. And after equilibrium, this is the observed integration. And I hope this integration after equilibrium to be close to this 45-degree line as much as possible. That kind of shows that my prediction matches the reality. And it's kind of true, actually, I think, except for the field of artificial intelligence, which is quite weird. Almost somehow other fields show that the predicted integration matches well with the observed integration. But of course, it's not conclusive. It's just there might be better ways to evaluate our theorem. Particularly, this is observational study. I had to do a lot of assumptions. I had to do a lot of estimation. I couldn't see which connections are made in phase 1 or phase 2. But it's somehow nice to see that the predicted integration after equilibrium somehow matches the observed integration, at least for a few, or at least for most of the clusters. And just based on the estimated parameters, we could do some counterfactual estimation that says if triadic closure or second phase connections is responsible for 3 to 5% of the network integration. So in the case we didn't have triadic closure, we would miss like 3 to 5% of network integration. And that's quite nice, I think. So, you know, now that we know that triadic closure might be a good candidate to intervene on, we would like to maybe have recommendation like this, like it. And I don't know, this is the online setting, but in offline setting, you might think of, for example, dormitory assignment. People have common friends and they might come up together in a single, in a common room. And we know that this kind of connections and this kind of recommendations can be helpful. And the next question is, how can we actually intervene on the network? How can we, for example, intervene on the phase 1 or phase 2 of the Jackson-Rogers model? We did something here. We studied interventions on phase 1 of the Jackson-Rogers model. Let's say, I don't know, you're the school administrator and you have the chance to decide about the initial room assignments. And then we studied, we provided some analysis about the short and long-term effects of interventions. Also, what are the optimal interventions where you have some constraints on the network, something we call the stability constraints. But I will refer you to the paper we have at EC for further info on this. Okay, looking forward, you know, I just studied triadic closure as one of the most common social processes we are aware of. And I consider triadic closure in the presence of homophily, but homophily is not the only thing that is affecting segregation. There might be other phenomena that are also affecting segregation, and their interaction with triadic closure might flip the sign of the effect. I don't know, but that might be interesting to see other theoretical study of the interaction of triadic closure with other well-known social phenomena. I also spend most of my time on very specific notion of network integration. It would be nice to see other things. I also mentioned that my empirical evidence is based on observational data and a lot of assumptions. It would be nice to see some interventional studies. Yeah, it would be nice to also see theoretical study of interventions on triadic closure with other constraints on networks. Like we had very simple setting where we had a simple stability constraint. And yeah, that's all I wanted to say. Thank you for joining me.
Thanks for the great talk, Ali. If you have any questions in the audience, feel free to unmute yourself and ask.
So feel free to reach me out, my email, if you have any follow-up questions, I would be more than happy to address them. Oh, I got something in the chat.
Thanks. Yeah, I'm gonna stop recording.